Hello. Welcome. My name is Francis Duranceau, and welcome to this talk about C# tips and tricks. It's not just about tips and tricks, but it's also about telling you how to profile by yourself and figure when you should optimize your game and when not. So there are also good news as part of this talk. I'm going to talk a little bit about what is coming in 2017.1, some of the new features. Eventually, I'm going to switch over to really how it works under the hood in C# when you compile what's really happening. So we're going to talk about different techniques like marshalling, but also under the hood features of C# like boxing, what really happens when you do a Foreach, a stack versus heap allocations. And finally, we will look at one example. Most important thing to remember is that we're going to talk about a lot of optimization tricks, but you should only use them when there is a bottleneck or when you're at runtime. If you're in your menu, it probably doesn't matter because performance is not an issue. So keep that in mind because I'm going to say things that do not make sense for a menu but make sense at runtime. Good. So let's go. The C# compiler. The C# compiler basically will take the C#, transform that into IL, intermediate language, and everything is running on top of a virtual machine that is an abstract stack machine. So we put instructions, we put operands onto a stack, and then we do instructions on everything on the stack. So it keeps pushing and popping operands on the stack. That's how it works. Everything else, the steps for the compilers are very similar to any other type of compilers, as I've listed here, going from source file, becoming like a tree builder, abstract syntax tree, and so on, until we get to the final IL. And then the intermediate language is either used by the just-in-time interpreter, or it's going to be ahead of time compiled for platforms like iOS or PS4, for instance. This is a very simple example of one function that is a very simple condition. We look if a value is larger or equal than 0, and then we return an input. Well, we just do some math on the value, and we return that. On the right side, this is the code that is generated. This is the IL. And as we can see, on the third line of the code, we see, well, first we load an argument, then we load a 0 on the, as an integer, and finally the third line, it's BLT, branch lower than, and it's looking at those two operands that are loaded on the stack. And then we continue to return either the value multiplied by 2 or the opposite of the value. This is a very simple example, but when we look at this, we see that it's pretty much only doing what we wrote there, right? The problem is that sometimes C# will generate instructions that are hidden there. And what I want to show you is how to catch some of those hidden function calls in the IL. The IL, when you're using IL to CPP, what we do is we take the intermediate language and then we convert that over C++. The good news is in your directory, in your temp directory, basically, if you look at the bottom of this slide, you will be able to find the generated C++ files that IL to CPP is generating. So we take the IL, convert that to C++. And as we can read here, it's basically looking at an input value. If it's smaller than 0, then we do something else. Well, actually, we jump to another label otherwise. So we do the multiply by 2, or we do the minus input value. It's very much the same. It's also an easy way for you to look at the generated code and really understand what the C# compiler did for you. (2017.1). If for those of you who have downloaded the experimental, the first beta, you notice in the project settings that you can switch to the experimental version of .NET 4.6. What does that mean? Why is it so exciting? My opinion, mainly because of all those new libraries that you're going to have access to. Nevertheless, there's also some caveats. Tasks and async, you cannot interact with most of the Unity API because it's not thread safe. So it will throw exceptions, very much like if you call those functions from other threads today. Good news is we are also introducing like a Unity C# job system that will still let you do a lot of multi-threaded operations, but that's the topic for the talk that I'm giving tomorrow. Nevertheless, data contracts, cryptography, networking, those will be game changers. On top of .NET 4.6, we also support C#6, modern C#, and those are only a few of the features that are going to be available. The very first thing I did when I downloaded the first beta, I gave it a try. I was like, are we really supporting these things? We do. Here, it's a very simple example where in my awake function, I have 5 debug logs where I'm basically testing the, well, those features, the null conditional operator, auto property initializers, and the expression bodied functions and properties. So the very first debug log on line 15, basically I'm looking at my last awaken object name string to figure if it's null. If it's null, we're just not going to print anything. Otherwise, if it's not null, then we're going to do a 2-upper and print that. Console says null. Makes sense. Let's assign a name to that string now. As we can see, now after assigning the game object.name, if we do once again the debug log, it was attached on my main camera game object. It works. Now, if we do a debug.log on my name, by default, it's auto property initializer that is set in the string my name. This is what we get in the console. If we change that variable, assign it to, once again, game object.name, what is getting printed? The main camera, not in uppercase in this case. And finally, the very last line at line 33, when we do the debug log on the text string, as you can see, the string is actually a string.format where we basically actually do a function call. And as we can see in the console, the result is embodied function example. So those are new features that you're going to be able to use now. Features of C#6. And then what? So after we're going to support .NET 4.6, our goal is to support Net Standard 2.0. bunch of new features that you're going to be able to use, many more libraries, so just more power for you. Make even better games, even faster. Nevertheless, there are still some questions. What platforms are affected? Easy answer, all of them. Some of them are still restricted to be AOT, ahead of time compiled, but that's not a surprise. Some platforms will still continue to support both Mono and IL2CPP, like Android, for instance, but iOS and WebGL will continue to be only IL2CPP. And IL2CPP supports all of the new .NET 4.6 features. So no problem there. What about the new garbage collector? That's a question I often get. In 5.5, we introduced a new compiler. In 2017.1, we introduced a new runtime. And in the future, only will we introduce a new garbage collector. The new garbage collector is going to be generational, which means that you'll be able to do like partial collect or collection over multiple cycles, and there's a lot of systems under the hood that makes it more efficient. But we only do baby steps because we want to make sure that when we're going to release the new .NET 4.6, it's going to be stable. And then, when it's really going to be stable, only will we move forward. Another concern. Here in Korea, especially, there's a lot of mobile games. You have to consider that because .NET 4.6 has many more core libraries, the downside is that the size of your build is going to be slightly larger. But that's only true for now, because in the future, we still want to get builds smaller and smaller and smaller by being able to strip the libraries that you're not using, by stripping part of the engine that you're not using, by just being better in general at stripping unused code in your games. This is an experimental, so please report bugs. If you find anything, any crash, help us help you. Report those bugs, we're going to track them, we're going to fix them, and it's going to benefit both of us, all of you, and also Unity. Often, I hear people saying that .NET is slow over C++. I come from an electrical engineering background where I was doing really, really low-level programming, where every single bit counts. So when I started at Unity, I was like, there's no way I'm going to do C#. I will do everything in C++ because it's more optimized. Until I learned about marshalling. What is marshalling? Marshalling is basically transferring data from the managed side to unmanaged memory, which means from C# to C++. Or I'm going to use unmanaged or native. I can change use one or the other word, but it's the same thing. And there are sometimes reasons why you want to use C++ or native, because you want to do better memory management, thread synchronization, or security, or just because you want to access drivers like a printer port or external peripherals that you already have in native library. So in some cases, you still have to use unmanaged code. But let's look at what marshalling really involves. Or how to do it. It's fairly easy. You create a DLL, put that into your libraries, and then write a C# file that is going to do DLL import your function, and you should be able to call that from C#. If it doesn't work, we're going to throw a DLL not found exception. But we really make it easy. You should be able to see this import dialog as soon as you import your DLLs. So at least you know that it's there, it's for the right platform, and so on. Where you have to be more careful is if you want to invoke unmanaged code, what's going to happen is we're going to call a get proc address. We're going to look up for the function call, and then only are we going to execute it. Which means that your function signature on the DLL side has to respect the C ABI, the Application Binary Interface standard. Or more simply, if you want to invoke C++ code, just use the extern C keyword and make sure that you're respecting the calling convention. Still, there are some issues. Runtime exceptions, they do not transfer well from C# to C++ and vice versa, because the exception systems are completely different. So you cannot mix and match exceptions from managed to unmanaged and vice versa. That's warning. Don't do that. When it comes to marshalling, really what happens now that you're able to call your functions, if you call a function and then you have a lot of data as parameters that you want to transfer over managed to unmanaged, most cases, it's simple. It's just blitting memory, so copying memory. That's true for all the simple types: byte, integers, floats. What about bools and strings and arrays? The problem with these more complex types is that the memory layout is not the same. If you look at the C# language, Boolean is actually emulated. It's not a native type. Strings are objects with indirections. So when it comes to those types, what we have to do is we cannot just copy. We also have to copy and change the memory layout. So those are the expensive types to transfer from managed to unmanaged and vice versa. Also, another big warning, be careful with memory management. In C#, fairly easy. The garbage collector does it for you. If you then keep a reference on memory in C++, looking at memory on the managed side, you never know when the garbage collector is going to collect everything, and then your pointer is looking at garbage. Same thing the other way. If you allocate data in C++, transfer the information back to C#, C# doesn't know when you're going to deallocate the memory. So be careful, and if you are going to exchange pointers on both sides, make sure that you have a good system to track when memory is getting allocated and deallocated or freed. But ideally, just don't keep references from one side to the other. It's probably a best practice here. Those more complex types, how do we manage them? So there are multiple ways, but basically you should use the marshal as, and then you explicitly say, okay, this string, I want to manage it as an ANSI string, or as a unsigned int, or as an unsigned short. So the marshal as lets you define how to transfer information back and forth for the complex type that needs a new data layout. Structs simple because they are sequentially aligned by default. It's not true for classes. And it's not going to be true either if you then have arrays or strings, because then there's going to be indirection, which will not match on both sides. For those cases, you will want to use keywords like the struct layout, layout kind, sequential tags, for instance. But I'll show an example later, a very simple one. We already said that. Memory that is owned by the CLI will be managed by the CLI, and when it's managed by the native side, it's managed by the native side. Don't cross the streams, ideally. That's it for that slide. So even though we talked about all these things, the most important thing is there's going to be memory being copied, which means that there's a cost when you're doing marshalling. If you're transferring a lot of data back and forth, really be careful, because that's going to be kind of a hidden cost. Even though your C++ algorithm will feel like it's much faster, when you really understand what you're doing in C#, it can be as fast. And the marshalling cost is going to be hidden, so really be careful. It's not always a very valid reason to just do managed code for performance reasons. You should do it when you have no choice, basically for memory management issues or accessing specific hardware or security reasons. Once again, if you do that in a menu, doesn't matter. At runtime, it may have a significant impact. Very, very simple structure in C. I have a bus structure. I then have a function where I calculate the health of actually multiple buses. And finally, I have a last function that is bus dead, that is returning a Boolean function. We remember, Booleans, it's not a type by default in C#. So let's look at what the marshalling is going to look like. For the first function, easy. Well, for the first function, the sum bus health is actually the second on this slide here. Nothing. It just worked as is. See, we had a bus star buses for the sum bus health. It turns out to be an array. If we look at the function on top, though, we had to add the return marshal as unmanaged type.u1, unsigned 1 byte, for the Boolean, is bus dead. And then only can we make those calls. And then it looks perfectly transparent. Nevertheless, here, when we call the is bus dead, we have to change the data layout. For the sum bus health, it's just memory copying. It's good? Let's talk about some of the best practices. I will repeat it to make sure it's clear. Those micro-optimizations are important, but only if the profiler tells you that there's a bottleneck. If you don't have performance issues, you should probably not pay attention to these things. Boxing. Very simple example class here, where we take the horizontal input, store that into a float value, and then we call debug log. So in my update function, I have only 2 function calls, right? Let's look at the generated IL code. Here, it's hard to read, I agree. Nevertheless, I've highlighted in green 3 function calls. Input get access, number 1. If you go at the bottom, there's the debug log function call. But there's also another one in the middle here, the box. We didn't call any function calls. Why is it there? The reason is we have a float for our value. We then call debug log that is actually taking an object as a parameter. So we have to convert the float to an object, which is why we call the boxing function. We didn't see it coming, but it's there. And it's going to allocate memory. It's an object. It's a class. It's going to be allocated on the heap. If you do that often, it means that you may trigger the garbage collector. Be careful with boxing. Foreach. If you go on the Unity forums, you'll see all over the place that you should not call the Foreach loop because it's going to allocate memory. Is it true? Let's have a look. This is a very, very simple Foreach. I have an array of integer. This is the generated code by the compiler. It's transferring my Foreach into a for. Very simple example, but I don't see any allocations here, right? So the truth is, there can be hidden allocations, but it's going to occur only when you're going to have to do boxing with an enumerator to go over collections. I had an array, no problem. If I'm using a collection, like we're going to see later, then we're going to have allocations while you call a Foreach, which means that if you write a simple for, at least you know exactly what's going on. There are tricks. If you call a collection, the problem is that you're probably using a generic type. And as long as you define the generic interfaces for like the IEnumerable and IEnumerator, you're going to be able to get rid of those allocations if you follow those rules. And you're going to get the slides after the presentation, so no worries. If you follow the rules, then if you do this call, here I'm doing the exact same for each, but now on a collection instead of an array, you're going to see that to get rid of all the allocations, I have to do a couple of things. Explicitly specify the enumerator for an integer, and also use a struct instead of a class for the get enumerator, so it goes on the stack and not on the heap when I do the return new enumerator. We'll see that the result of writing my class is definitely more verbose, but it works. Should we use classes or structs in general? I gave you some hints, but if we look here, I do, in my update function, I have a point structure. The first line, I don't call new or anything, but it's there. Second line, I call a new on my point structure. Third line, I call a new on a point class instead of a structure. Let's pretend that we don't know what's going to happen, and let's just look at the results of the IL. I'm not going to go through the resulting IL. It's fairly complex. Nevertheless, if we look carefully, in the first few lines, we're going to realize that we actually load the struct onto the stack, which does not interfere with the garbage collector. For the class, though, it's in red at the bottom there's a new object being called, which means that we're going to allocate that onto the heap. And at the end of the function, obviously, it's going to be released. But nevertheless, we may be fragmenting the memory. Or if we do these type of operations in a very tight loop, we may literally trigger the garbage collector. In general, we will prefer using structs over classes, simple types over complex types. Yeah. Another warning, strings. Strings are immutable, which means that whenever you do string manipulations, there will be a copy. They are objects, so they will be on the heap once again. So in general, the recommendation is to use string builder, which will create a buffer, and then we'll use that buffer to do all the manipulations ahead of time. And that's for when you really have to use strings. In some cases, it's probably better to just avoid using strings at all. So when the Unity API is telling you that, hey, if you want to do a material that's set color or animator that's set trigger, and then it's using a string, a lot of the Unity APIs also have the option of using a hash function. So as you can see here at the bottom, I'm using a static read-only integer. I'm converting the result of like what is associated with the string, and then I'm using the hash to do the binding, and it's just an integer. So no string manipulations, no string passing or copying or reference or anything. We're done. I love this one. I started using Unity in 2010. And then, back then, on the forums, people were telling me, oh, so if you want to clear up your memory, you have to call the garbage collector 6 times. I was like, where is that coming from? And then, on a different forum post, other people were saying, like, no, it's not 6, it's actually 7 times. I was like, where are those random numbers coming from? Is it even true? The answer is no and yes. It's confusing. So by default, if you call the garbage collect only once, you're safe. But if you call it and then it's platform dependent 6 or 7 times, there is another hidden behavior. It's simply that if you call it multiple times, the garbage collector is going to be able to decommit memory from virtual memory. Do we really care? No. It's only nice to release memory that could then, like virtual memory, that could then be used by other application in your OS. The truth is, unless you load the game, allocate, I don't know, a gigabyte of memory, and then only use like 100 megabytes, that would be nice for you to do so. But if you do that, there's something wrong. Like, why would you allocate a gigabyte to only use 100 megabytes later? So by default, we don't really care, but at least now we know where those magic numbers 6 and 7 are coming from. Another thing to be careful of, when you call vector.0, for instance, you may feel like it's completely free, right? Almost. If you pay attention, actually, there's a new object call here. So at first I was scared. I was like, are we really allocating something on the heap? In the case of vector3, the good news is that because that's a structure, it's going to go on the heap. Nevertheless, when you call vector3.0, you're still doing a virtual call, which when you do it over and over and over, it's costly. So you know what? You may actually want to cache values like vector3.0. Or, for those of you who are going to be there for the C# job system talk tomorrow, use new types that we're going to introduce, new intrinsic types, like float3, for instance. OK. And then I was looking at a game a couple of weeks ago, and the people were using a game manager using the singleton design pattern. And they were having performance issues. So let's look at an example together, and then, bear with me, this is on purpose. I will lead you into a big mistake, only so you learn a lesson at the end of the talk. OK? So I'm tricking you. It's a trap, I tell you. The singleton, it's a good example because it's the type of call that you do often. It's something that if you look in your update function, you could call like multiple thousand times. So I think it's a good candidate for those micro-optimizations we were talking about, right? It may be a little bit hard to read, but here what we're doing is we have a static game object that we use as, and then we compare that value whenever we call our instance function. If it's null, then we're going to create, we're going to either find the game object that we want this singleton script to be attached to. Otherwise, we just return the instance that we have here. So we have a game object that we compare with null. Basically, this is what we will look into over the next few slides. Generated IL, as we can, without going through the whole code, what is interesting here is that when we do the game object equal null, the comparison to figure if we have to find the instance or create a new one or just return what we have, we're calling the operator equality that takes two Unity Engine objects, types, as parameters. And then we compare them. So if we look at the result in the profiler, I called my singleton gamefind.get instance 10,000 times. It's taking 21.7 milliseconds on my MacBook Pro. So not the best computer, but it sounds like very, very slow. And if we dig down, because I've enabled the deep profiling here, we can see that we have a function called object is native object alive that is taking 6.5 milliseconds itself. So my first reaction was to think, well, let's not do a game object comparison in my singleton instance function call. Let's just have here my static singleton game variable instead. Instead of a game object, it's just the type of my class. Here, it's not a mono behavior. There's no more game objects. It's just plain, simple C#. So here, what I do is I look at the instance of my class, my variable, if it's equal null, and then I do the very naive implementation of a singleton. If we look at the profiler data, what we can see is that now, when I call that function 10,000 times, it's taking 6.22 milliseconds, while my first, the other call was taking 21.7 milliseconds. So it's about like almost 4 times faster. But and then I went and looked into the IL of my isNativeObjectAlive function call. And there are 3 lines that are interesting. There's the get cached pointer. There's the line that I highlighted in red, which is just basically loading 0 on the stack of the VM stack machine. And then there's the operator inequality. Why are those 3 lines interesting? It's because if we go back here, we can see that isGameObjectAlive is taking 6.5 milliseconds. The operator inequality is taking 0.35, and then the get cache pointer is taking 0.34 milliseconds, which means that there's about 5 milliseconds missing. Do we agree? More or less 5 milliseconds. So looking at this, I was like, it can only be the loading of the 0 that is taking 5 milliseconds. Really? No. And this is the mistake that we did. The problem is, I profiled everything in the editor. Never, ever profile in the editor. Why is that? Because this is the source code of the isNativeObjectAlive. Basically, first line, if not in the Unity editor, else we do a lot of stuff. So the IL that I was looking at is not exactly what I was profiling. My lesson is always make a standalone build. Always. When you make a standalone build, you cannot necessarily profile, do the deep profile. So I highly recommend that you use the custom sampler. Here, that's basically what I did. I begin measuring my singleton call, and then I end right after. It will then appear in the profiler. If we look at the results now, the find, the first implementation is taking 3.12 milliseconds. Why? There's the conversion over to like objects to do the comparison. There's probably also virtual calls that are being called. Second implementation is taking 0.58 milliseconds, totally reasonable. And then I was wondering, is the fact that I'm calling a property on my instance function, may it have an impact? Looking at the results, not at all. I said that. Never profile a game running in the editor. Always make a standalone build. I looked quickly at one of the new feature of C#6, the exclamation mark operator. I was wondering, is there an impact on the generated IL? Side by side, it's almost the same. There's only one branching of difference between both. So then, when you know how to do that, you can then figure by yourself which feature of the language you want to use, and also, more importantly than anything else, where in your code. Because as I was saying, a tight update function call during gameplay is not the same as when you have code running for loading assets or in the menu. Mono behavior or classes, should we use one or the other? If you're not using the awake, the start, and the update function and these type of things, you should probably use a class, simply. If you're not convinced, you should search on Google 10,000 update calls, Unity, and you're going to find a blog post by Valentin Simonov, our evangelist in Russia, who's detailing, really giving into details the pros and cons of calling modal behavior scripts or not. Should we seal our classes? The answer is yes. Because in some cases, when you do like a collection of sealed classes, in some cases the compiler is going to be able to know that there's no potential inheritance, which means that we're going to be able to get rid of some virtual calls and make calls directly to the type of the object. If it's not sealed and you have a collection of animals, for instance, the problem is that the animal, you never know, will it be like a cat or a dog? So you're always going to have virtual calls in between. Should we call static or not? I haven't seen any difference. Should we use the unsafe keyword because we believe that there's not going to be any optimization? If you use struct and native, it makes no difference. Should we use link queue? It creates a lot of overhead. So in general, I would say avoid that. And then we could argue if it's sugar syntax or not. But if you're in your main menu and then you're filtering through lists of items, go for it. If you're at runtime, it may have a significant impact. Same thing for the generic types. It's always simpler for a compiler to optimize when you know the type than when it's generic. So once again, when you use generic, a lot of overhead code is going to be generated in the IL. Just be careful and know when you want to optimize or not. And finally, as we said, a lot of the C# keywords can be hiding overhead and allocations. You will want to use plain old data in general, so struct over classes, int, float, struct. And when you're not sure, just look at the resulting IL. And if there is one final word for this presentation, only profile when you look at the profiler and you see a bottleneck. Otherwise, you're working for nothing. Thank you very much.